Hi, welcome to this lecture on mathematical methods. Today, we are going to discuss a new topic which is called Fourier series. So, the title of the lecture is Fourier series. The question we will answer is, can I write an equation for any function? This is the question that we would ask. If you think about doing an experiment and you collecting some data. So, let us first think about you are collecting data as a function of time. Let us say you are measuring concentration as a function of time in a particular cell, or you would want to measure some specific property as a function of time. There are 2-3 ways this can happen, and one of the ways is that this function could kind of increase and decrease around some average value, or it could show some behavior, it could show some arbitrary behavior. So, if you have a data which is kind of arbitrary, so if whenever you have a data which has some shape, arbitrary shape, we don't know what equation to write for this. Right? What is the equation for such a curve? We don't know. Can we write an equation for such a curve? That is first question that comes to everybody's mind, and we will see what we can do if you have some data which looks kind of arbitrary. That is one thing. Second thing is, we will have various structures. For example, we will have structure of a protein, we will have structure of DNA organized chromatin, we would have concentration in a particular manner. So, or we would have cells organized in a tissue. If and when we have such structures, can we write an equation for this? For example, I have a protein, I have some protein, so we have basically atoms organized somewhere in a 2D space here, but in general in a 3D space. So, this is my x and y. I am just showing a protein shape in a 2D paper, and these are molecules. So, these are molecules. So, the position of these molecules along this varies. So, this could be written as some function of x and y. Like, so, x in general, a 3D thing can be written as some function of x and y, or some function of x, y and z. So, any shape of a protein or any molecule could be written as some function of x, y and z. Now, can we write an equation for this? If you know the data, if you have the data, can we write an equation for this? The answer to this question is the following. So, there is something called, so this Fourier series will help us in this context. So, let us first understand what is a Fourier series. Fourier series is basically any periodic function f of x can be written as sums of sines and cosines. So, you have some function which is periodic function. So, what do I mean by periodic? Periodic means repeating after intervals. So, if you have a function which is repeating after some interval, then that function, that data, if it is repeating, I can use sines and cosines, and some series of sines and cosines I can use and write this function. So, this is the idea here. Now, let us think about it a little bit. What happens when you have, what are the contexts where you will have some data? For example, you would know in crystallography. What happens in X-ray crystallography? You have a protein, you have to crystallize it. What does crystallizing means? You have to form a crystal. What is crystal? Crystal is a repeating unit of the protein itself. So, you have many proteins arranged in a lattice in a periodic manner. So, if you put a lot of effort and pack this protein as a crystal, then you have the molecules of this protein repeating in space many times. This is like a periodic function if you wish. Now one can use these ideas from Fourier series and Fourier transform to understand this positions of these molecules in your protein, right? So you have, let us think of a particular protein having two atoms. So let us think of a simple, so you have, I am just going to think of a simple protein, so which has some shape like this. So this is a shape like this, which is like a inverted L. So I could have a repeating function of this. I could pack this protein in a repeating fashion here. I could pack this protein in 3D. That would be forming a crystal. So I would form a crystal arrangement. Let me show this here. So now here and here, so I would draw this and this, and here and here, here and here, and let me quickly draw this. This is I am just quickly drawing the repeating. So what do I have? I have this protein which is like an inverted L. Let us say this is the shape of my protein, and this is the folded shape of my protein. I have arranged this protein into nice lattice. So if I just take this green molecule, if I go from some distance to the right, I can again get this green. If I go some distance to the left, I can get again to this green. If I go some distance top, I again see this green circle. If I go some distance down, I again see this green. So this green atom here or green molecule here is periodically arranged. Similarly, this red, this is periodically arranged. So each of this, if I just take an atom or a molecule, which is a circle here, it is periodically arranged in space. So if this whole thing is like a periodic function, if you wish. So if I have such periodic function, which is like a crystal, if you wish. So you have a nice crystalline arrangement, a periodic arrangement. Then we can use sine and cosine that we learned. What are sines and cosines? They are periodic functions. They repeat as a function of x, right? So this is the idea that we can use some combination of sines and cosines to describe any periodic function. How do we do that? It is the following. So it says that any periodic function f of x, so first we will do in one dimension. F of x is a function which is like a repeating function of a crystal like we saw, for example. This can be written as basically a0 by 2, which is a constant, plus an cos nx sum over n. I will explain what does it mean. Bn sin nx sum over n. So this is the series, and let me explain this. What does it mean? What are we saying here? We are saying if you have some function, f of x, this can be written as some constant, which I could call anything, but I am calling a0 by 2 for convenience, but I could call this anything, plus a1 cos 1x plus a2 cos 2x plus a3 cos 3x plus dot 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 is an infinite series up to infinity, plus I have b0 sin 0x. So b0 sin 0, since sin 0 is 0, I will not have a b0 term. I will have a b1 sin 1x plus b2 sin 2x plus b3 sin 3x plus dot dot dot. So I have basically an infinite series of sines and cosines. I don't know what are the values of a1, a2, a3, b1, b2, b3, etc. But if I know this a0, a1, a2, a3, etc. and b0, b1, b2, b3, etc., I will get this. I will get a formula for f of x. So if I know, so a0, a1, a2, a3 are unknowns, And if I know AIs, these are some set of values, and BIs, these are another set of values, we can get this f of x. If I know AIs and BIs, we can get f of x. This is the basic idea that we would learn. Now let us see how do we do this. So let us look at this again. So let us look at this again once more. If you look at this series here, if I know, let us assume that we have only two numbers which is a constant and all other numbers are 0. So let us assume that, so our function, let us assume I know a1 is equal to 3 and b3 is equal to 5. All other a's are 0. All other ai's equal to 0. All other bi are 0. So other than this a1 and b3, all other coefficients are 0. So if I take this equation f of x, I have a1 which is 3 according to me. So if I have this 3, so I have 3 cos x, and this is 0, everything else is 0. And I have b3 which is 5. So I have 5 sin 3x. So I have my equation, my f of x, if I have only a1 is equal to 3 and b3 equal to 5, if I substitute in that expansion, what do I get? I would get f of x. So please go back and look at this expansion. I am saying a1 is equal to 3 and b3 is equal to 5. Everything else is 0. If I specify these two numbers, I get a function which is essentially 3 cos x plus 5 sin 3x. So I have an equation by specifying these two numbers. So if I specify these two numbers, I have an equation for a function. This could be my protein, for example. The protein expression could look like this. This is some function. I can specify this, for example, I can plot a graph of AIs versus I and BI versus I, and I have only a value, so only when A1, so this is 0, 1, 2, etc., I would go. Here also I would go from 0, 1, 2, etc. So when A1 is 3, so what does it mean? A1 here is, this value is 3. All other values are 0. Only this is 3, all other values are 0. Here, the next one is B3. B3 is here. So this is B3. This is my 3. So B3 is 5. So B3 is 5. So if I have this two peaks like this, so there is this and this two peaks. So what I have just essentially, I have basically a graph which would specify AI versus I and BI versus I. I can specify some peaks here. I know if I specify just this for a particular I value, here I is equal to 1 and I is equal to 3 here. If I specify this kind of a graph, correspondingly this would imply that my f of x is 3 cos x plus 5 sin 3x. For example, if this is the thing that we just described. So basically what am I saying? If I specify AI and BI, I can specify a function f of x. I could specify many AIs and many BIs, then I would get some function f of x. There are infinite numbers, but if I specify only the most important coefficients, the dominating coefficients, that function. So, if I just specify only most important dominating coefficients, so I have this full number set of A0, A1, A2 up to A infinity, B0, B1, B2 up to B infinity. If I specify only some of them, I specify most important values. How do we know important? We will discuss that later. If I specify some important values, then my f of x can be approximately written. I am specifying only some values, I am not specifying the infinite values, I only specify important values and I can get approximate expression for f of x, and that approximate expression could look roughly like your real curve. So, this is the first idea that you should come to your mind. This also has another connotation. Instead of specifying the whole curve, I could specify some two numbers. Let us say I have a data which looks like, so we had this curve example equation. So, let us say we had this equation which we just described, which is f of x is equal to 3 sin x cos x. So, what we wrote, f of x is equal to 3 cos x plus 5 sin 3x. So, this is the equation that we wrote, and this, if I have this as a data, so if I plot it, this would look like some curve in space, it would be some oscillating curve. If I have some data, if I want to specify this as a data, I would need various numbers which is varying in various ways. I don't know, let us say I have some data like this. I have to specify a lot of data points to describe this. Instead of specifying all these data points, I could just specify some numbers like A1, B3 and some numbers like this. If I specify, like it could be I, some numbers, some A k, whatever k could be something, and if I specify some bk, that would be equivalent of specifying this data. So, I could either specify this data which is a function of x, or I could specify this ak and bk or ai and bi. So, I could either specify this or specify this function. Both are equivalent and one would give us the other. This is the first point to remember. So, we have an expansion, we have a series expansion where if I specify some coefficients ak's and bk's, ai's and bi's, an's and bn's, I would have some function specified. Now, the reverse question we can ask, if I know the function, can I get ai and bi? So, this is something that we will quickly learn. If I specify a function, can I get ai and bi? It turns out that you can get. So, just to understand quickly how do we get it, you can imagine this little bit like a vector. So, we had, think of a vector A which is a1i plus a2j plus a3k. If I want to know the value of a2 given A, I can write a2 is a dot j. This is something in vector one would learn in school also. If I take a product of this, dot product of this, a vector and j, I would get this function a2, this value a2. Similarly, a3 I can get a dot k. So, a3 will be a dot k. So, similarly, I have now a function f of x where I have a0, I would write a0 by 2 here, plus a1 cos x plus a2 cos 2x plus so on and so forth, a3 cos 3x plus dot 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 dot. Similarly, b0 is 0, b0 is irrelevant, b1 sin 1x plus b2 sin 2x plus b3 sin 3x plus dot dot dot. Now, if I want to find out a2 here, this a2, if I want to find out this a2, what you have to do is multiply this f of x with cos 2x and integrate. If I want to find out a2, multiply this f of x with cos 2x and integrate. That is, if I want to find out b2, I would multiply f of x with this sin 2x and integrate. So, if I know f of x and if I want to find out any of this coefficient, take the corresponding sine value or cos value, multiply this and integrate. Think about it. So, if I write it as an equation, this is what it means. To be precise definition, f of x is written as this way, a0 by 2 plus sum over n an cos nx plus sum over n bn sin nx. If I want a0, I would multiply this f of x with cos 0x. Cos 0 is 1. So, this just integral of f of x will give me a0. If I want a1, I would take f of x, multiply with cos 1x and integrate. If I want a3, I would take f of x, multiply with cos 3x and integrate. Integral is from minus pi to pi, divide. This is the typical definition. Similarly, if I want bn, let us say b3, I take f of x and multiply with sin 3x and integrate. If I want b7, I will take f of x, multiply with sin 7x and integrate. So, if I want any bn, I take f of x and multiply with sin nx and integrate. For an, I multiply with cos nx and integrate. This works because of some particular property of sine and cos, which we wouldn't go into the detail now, but just to say that this sin mx, sin nx, if I multiply, they are 0 if m is not equal to n. This is what this delta mn means. Delta mn is 0 if m is not equal to n. This is 1 if m is equal to n. So, this have some value only if m is equal to n. That is why this works. Similarly, cos m and cos n, if I find a product and multiply and integrate, this integral is 0 if m is not equal to n. Similarly, sin m and sin cos, whatever be the m and n, is always 0. So, this is the property that helps us to do this trick and help us to solve and understand, to obtain this. So, what did we say? We said two things. If I have a periodic function f of x, I can write that function as a series of sines and cosines. If I know some coefficients, which is a0, a1, a2, a3, etc., and b0, b1, b2, b3, etc., I can precisely write the f of x. If I do not know this a0, a1, and a2, but I know the f of x. If I know the f of x, I can also back calculate this a0s, a1, a2, a3, and a4, etc. Now, the question is, if I specify a function, can I get basically if I specify a function, can I get a0 and a1, a2, etc. So, we would start with some very simple periodic functions. So, we would start a function which is like a straight line. So, I have a function which is just like a straight line. This is my function, and this function would repeat again. Then this is repeat. So, I just take a straight line and make it repeat many times. So, such function is called sawtooth. This is like a sawtooth. So, this is a sawtooth function. So, this is what I would describe. So, we would take a sawtooth function. this function has this form f of x equal to x, f of x equal to x for value from minus pi to pi. So I would take, so if I just take this I would call as minus pi, and this point I would call as pi. Minus to pi, this is like x, and otherwise it has no value, and again minus pi to pi repeat again. So this is a repetition of this function, a straight line. This is a repetition of a straight line function. So imagine that your protein is just like a rod, which is like a straight line. Now we have many copies of this. You form a crystal like this. So you have a crystal now. How do we write a mathematical equation for this? Alright, that is the question that we would ask. So it is done the following way. So our function is f of x equal to x, and f of x plus 2 pi is f of x itself. It will repeat. That's what it means. Now I can calculate it, take this x and integrate from minus pi to pi. I will get a0, which will turn out to be 0. I can calculate an by doing this integration. So specifically look at integration. I can integrate x cos n x dx, and you will get 0. So all an's are 0. I can get bn by doing this integration, and when I do this bn, I would get minus 1 power n plus 1 by n times 2. This is the answer of this integral you will get. Check this carefully. So I only have bn values now. So I can write this series only bn's. So only sine series, a series of sines. So I would write this series, and I have an infinite series now. I take one term by one term and plot. If I take the first term, which is 2 sin x, I plot. The sawtooth function is in blue and the first term is red. So I would get a function which doesn't look like a blue, but somewhat like that. If I add two terms, it is 2 sin x minus sin 2x, I would start getting somewhat slightly better. I add 3 terms, I would get slightly better. I would add 4 terms, I would start getting closer and closer to the blue, like a sawtooth it is coming. If I add 5 terms, so these are the 5 terms described below. These are the first 5 terms of that infinite series. So write down this infinite series and check if these are the 5 terms of that infinite series. You would get this nice sawtooth like function. So if I add 5 terms, I would get this nice function which is coming closer and closer to sawtooth. If I add 6 terms, 7 terms, it will be nice sawtooth. If I have infinite terms, it will be a perfect sawtooth function. So if I take first 5 terms, I would get this. So I can write an equation for the protein which is a repeating function like this. I could write 2 sin x minus sin 2x plus 2 by 3 sin 3x minus half sin 4x plus 2 by 5 sin 5x. This equation written here is an equation which is a function which can be approximated to a sawtooth like function. I can write more terms and get more precise function. I will play a quick movie here which would be adding more and more terms which would make it closer and closer to the sawtooth function. So let me play this again. First term, second term, 3 terms, 4 terms, 5 terms. So with this I will summarize. We learnt a Fourier series. Any function, periodic function, can be written as a combination of sines and cosine. That will help us to write equations for any function. Think about this, view this carefully, read about this. This will help you to think about this, and we will, in the next class, we will say a little bit more about this. With this, I will stop here. Bye.